Yeah, we will continue with our lecture 1 from where we stopped last day. So, last day we were discussing about the draw stress for homogeneous deformation for a non-work hardening material as well as the draw stress required for the homogeneous deformation for a non-work hardening material with and without friction, and we ignore the redundant deformation in that case also, because this redundant deformation is something which we will discuss later. It is coming earlier also we have discussed. So, in the draw stress we arrived at was sigma d is equal to sigma dash log 1 by 1 minus r. So, that is equal to 2 by 3 into your uniaxial yield strength sigma 0 log 1 by 1 minus r. So, if you consider friction, so with the friction if you are considering with the friction sigma d, we can write it as sigma 0 dash into 1 plus b by b into 1 minus a final, the cross sectional area, final cross sectional area by initial cross sectional area raised to b, where b is equal to mu cot alpha, and alpha is the semi di-angle. This is what we have arrived last day. And you will find that these are not the two expressions, this is like say 1 and this is equal to 2, where several expressions have been developed for the draw stress required and other things. Okay. And if the material is work hardening, because this is just for a non work hardening material, if the material is work hardening, then this sigma 0, if the material is work hardening, the sigma 0 dash in the above expression to be replaced by the mean flow stress. Sigma bar, which you can get it, we have discussed sigma bar is equal to 1 by epsilon b minus epsilon a into say where sigma bar is equal to 1 by epsilon a minus epsilon b into sigma from epsilon b to epsilon a sigma d epsilon. So, these are the strain under which we have to study. Okay. So, this is a very using the average flow stress is a very convenient form of using that, if you know, because it is much more easy, because most of the time we have this expression sigma is equal to a epsilon raised to n. So, from this now we can derive it very easily. So, that is one very convenient form of using the average flow stress. If you have the flow curve of the material, that is the true stress versus true strain curve in the plastic region of the material, then this expression and replacing this stress component by the average flow stress will be the most convenient thing. And say there are many other expressions if you are considering this friction as well as the redundant deformation. A large number of work has been carried out, and with different materials, different diangles, different frictional conditions, and you will find that there is a wide range of this expressions, because material properties are coming into picture. So, it becomes very difficult to have a uniform relationship for that. But in spite of that, the draw stress necessary for the deformation, for drawing, the stress necessary at the exit for the wire drawing, considering the friction and redundant deformation, which was put forward by Seibel, which is of this form sigma d is equal to say sigma bar into, this is a widely accepted relationship, into 1 plus mu by alpha into log A 0, that is a initial cross section area divided by the final cross section area. Plus 2 alpha by 3, where mu is the coulombs, mu is the coefficient of friction, and alpha is the semi diangle. So, that way we can find out this is one of the expression, one of the relationship which has been widely accepted, but whatever be the type of relationship, when you are considering the friction and redundant deformation, the flow stress can be represented in a general way as sigma bar into 1 plus b into phi, where phi is your friction factor into your strain log A f by A naught. This is a general expression which we can represent it considering friction and redundant deformation. So, if it is equation number 4, and another expression is that say these are the two expressions which we can get. One is 1 plus b by b. So, because we are introducing this term phi into 1 plus, this is the relationship which earlier we found without considering the redundant deformation. So, in that also we can write, but only thing is that you are just considering this phi term to take into account of the redundant deformation. That factor is called as redundant work factor phi. Okay. So, this expression we can just write in a general form as d is equal to say beta, because if you eliminate all other things into average stress into your strain. Okay. That is log 1 by 1 minus r. Okay. So, we can write in this form, where beta is the factor, beta is a factor which takes care of your frictional loss and redundant deformation. So, that is why this beta is introduced, and generally the value of beta is between 1 and 3. So, where beta is nothing but the ratio of the total work including friction and redundant deformation to the work for homogeneous deformation. And this beta also, some people they express it as an efficiency factor 1 by eta, where this eta is a product of two efficiency term. One is eta phi due to redundant deformation, and this f due to frictional loss. At the die workpiece interface. Okay. So, that is how this beta is termed. Okay. The factor phi it is a function of your alpha and r, where alpha is your diangle and r is your reduction. So that is so we can call it as phi 1, which is nothing but phi 1 is called as the redundant work factor. Or that corresponds to the, so from this we can find it out, the enhanced strain corresponding to the yield strength of the metal, which has been homogeneously deformed to a strain of epsilon. Okay. So that is what from our earlier discussion we have discussed it. So that means, and phi can be estimated from the displacement of a flow curve after tensile testing of the drawn wire. So you have the wire. So before the drawing operation, you conduct a tensile testing in an annealed condition, and the same material you just do the drawing operation, and that wire again you test it after the drawing for after some particular strain, and then you will find that the yield strength has increased in the drawn wire. So you just displace it towards the right, so that it matches with that, and from that when it matches with the actual flow curve, what is that strain? That is the epsilon star. So from that we have discussed this part earlier. So how to calculate this redundant deformation? That is another important, because it is not that easy. What is this redundant deformation? When the metal undergoes deformation through the deformation zone for any material. So we are just now, since we are discussing about the wire drawing operation in a conical die, the material is deforming. We mentioned that if it is a homogeneous deformation, the square grid will be distorted to a rectangular grid, but depending upon the die angle and the friction conditions, you will find that okay, it is not a homogeneous deformation which is taking place. If the die angle is very large, then actually what happens is, after certain die angle, there will be an internal shearing of the material. So too much of extra work has to be done. So it is very difficult to arrive at or derive an expression for this redundant work or redundant deformation. The only way is that we have to carry out some experiments and then find out empirical relationships. Okay. So there are two, 3 methods by which this redundant deformation can be found out. Okay. So one is we can find out the redundant work factor. So that is phi, by people have carried out this expression and then arrived at this relationship, that is 1 minus phi 1 is equal to 1 minus exponential minus phi 2 b epsilon divided by 1 minus exponential minus b epsilon into phi 2 to the power n. So I will come to that what is phi 2. So if the product is beta and epsilon, so if beta b into epsilon it will be approximately equal to 4 mu by delta, where delta is deformation zone geometry, which you have expressed earlier. We have come out, I will discuss immediately also. And if this is sufficiently small, then phi 1 will be equal to, we can approximate as phi 2 to the power n plus 1, where n is the work hardening exponent obtained for the material, which is nothing but k epsilon raised to n. So n is equal to work hardening exponent. So this is what happens. Now one should be able to distinguish very clearly between phi 1 and phi 2. Many books know sometimes it is confusing, but one should be able to know what is the difference between this phi 1 and phi 2. So phi 2 is the redundant deformation, whereas phi 1 is the redundant work factor. The redundant deformation, this phi 2 is the extra deformation. See, for example, phi 2, if I am writing it clear, is the extra deformation or maybe say your this strain, which is the equivalent strain sustained by the drawn piece compared to the nominal or the homogeneous strain epsilon. So, just like if you are doing this, say for example, this is your basic flow curve, suppose this is your basic flow curve of the annealed material. Now, the annealed material is subjected to say drawing operation, and after a drawing with a reduction such that corresponding to a strain epsilon, then you take the tensile testing of that, you conduct a tensile testing, and you will find that your this flow curve has the yield strength has increased by some amount. Okay. So, this is the thing. So, but if you are just shifting this curve, if you are shifting this curve towards the right, if you are displacing towards the right, and so that now this comes and matches with this, then you will find that this is the total work done due to redundant deformation. So, but that corresponds to a strain, enhanced strain of epsilon star, though your actual strain, actual reduction in the during the drawing operation was strain, but you will find that now this is an enhanced strain. So, that is the equivalent strain which you are considering to that. So, from this phi 2 can be defined as epsilon star by epsilon this. So, that is the it is the extra deformation which is taking place. Okay. Whereas, this phi 1 is the stress due to the redundant work, the increase in stress due to redundant work. So, that is the difference. So, here you have an increase in the stress here. Okay. So, that is what is phi, whereas this is the strain which is coming. Now, you will find that if you find out, try to find out this the relationship between this deformation zone geometry and the redundant deformation, you can always find it a correlate in this forms. Phi 2 is equal to C 1 plus C 2 into delta. So, that is what, where delta is your geometrical factor which is coming. Okay. It is the average thickness to the length of maybe of deformation zone. So, that we have discussed earlier. Now, another method is you are also finding out the stress strain curve of the wire drawn under different conditions, and these are compared to your stress strain curve of the fully annealed wire. Okay. So, the same case which you have done, the flow stress of drawn wire is always higher than the annealed wire. So, that is what we have seen in the previous diagram. The strain is in simple tension of the drawn wire is thus equivalent to your epsilon star. So, you will find that epsilon star is linearly related to the nominal stress as a function of nominal stress epsilon and die angle. So, that means this is linearly related, that is K 1 into epsilon W or epsilon, if it is a wire only epsilon plus K 2 into sin alpha, where alpha is the die angle, and since earlier we have written this is equal to epsilon 2 phi 2 into epsilon. So, from this relationship we can arrive at say like if you divide it by epsilon, then you will find by this as phi 2 into epsilon, then and divided by epsilon, then we can get it as phi 2 is equal to K 1 plus K 2 into sin alpha by epsilon. So, where this K 1 and K 2 are experimentally determined constants. So, under different conditions you can find out what are the value of K 1 and K 2. and phi 2, that way you can find out if you know the value of alpha, and then this. So, the advantage of this, the significance of this equation is that only 2 data points are required for one particular value of alpha. So, if you just look at it, you will find, because in this case, no, from this you can find out what is the value of phi 2 with the different strain values, and if you get a 2 points, no, you can easily get it, and to enable k 1 and k 2 you can just find it out, and hence phi 2 can be calculated for. So, for determination for k 1 and k 2 to be determined, only 2 data points are required. For a particular value of alpha. So, hence this phi 2 can be calculated, can be determined for all diangles and reduction. This is the biggest advantage with this, because it is a straight line equation which is coming. Now, coming to this delta. So, delta, as we have discussed earlier, delta is nothing but the average thickness, ratio of the average thickness of the deformation zone to the length of the deformation zone. Okay. Now, see, this is the thing. So, if this is the wire drawing operation, you can have, say, maybe one is the plane strain condition. So, you can find out whether it is diameter or height. So, if it is strip drawing, then you consider this H0. If it is a wire drawing, you take this DO, and finally, the corresponding value at the output will be H1 and D1 respectively. So, we can find out this sigma s by this relationship, alpha by r into 2 minus r. Okay. So, that is based on the plane strain condition, where r is equal to, say, we can say r s is equal to 1 minus h 1 by h0. For strip condition, it will be based on this height h at the beginning, at the initial. Whereas, if it is for wire drawing operation, it is the diameter which is taking place. So, you will consider that r w is equal to this one. So, this r will be r w here, here it will be r s. So, r w is there. In that condition, you are getting this relationship, the deformation zone geometry, delta is equal to alpha by r into 1 plus under root 1 minus r the whole square. So, for wire drawing operation, this is the general relationship which people use it, and so and you will find that in different books, different ways it is being used. Okay. But from this you can also have a simplified form of delta is equal to 4 alpha by your strain. So, so that is how you find out this deformation zone geometry. Now, when you consider this, there are 3 factors. One is the homogeneous deformation, where there is no friction, there is no redundant deformation. If you just pull the wire, how it is happening and what is the energy required for that. So, that is called as the work for plastic energy. We can say energy for homogeneous deformation. Plastic energy we can say, where there is no friction, there is no redundant deformation. You just pull it, and from that you find out for a strain how much is the energy required. So, that is the UP. Now, if you just look at it with a diangle, let us say a conical diangle is coming. So, this with the die angle decreasing, two things are happening. See, for example, I am just getting from say maybe diameter of this to a diameter of this. So, this is the reduction which is taking place, and I can say that okay, this is going to be my die angle. Okay. So, this is your 2 alpha. This is the 2 alpha angle. Now, if with the alpha decreasing, when it is alpha decreasing, suppose let us say we want the same diameter, so this will be 2 alpha 2, this is 2 alpha 1, let us say. So, if these diameters are same, the output reduction is same, but with a different die angle. With a lower the die angle, you will find that the contact area between the die and the workpiece is higher for lower die angle. Whereas the die angle increasing, this distance, the deformation zone length keeps on decreasing. So, when the deformation zone length keeps on decreasing, the total contact area between the die and the workpiece, that decreases, because it, say as per this relationship, this figure, so these two cases are there, this is one and this is 2 case, second case is coming. So, that means with the increase in the die angle, the frictional loss keeps on decreasing, because the total contact area decreases. But you just consider the case with the increase in the die angle, what happens is that maybe the one is the die angle is like this, another is the die angle is like this. Okay. So, in this case the metal has to come like this and deform like this, here it is there. So, there is a sharp deformation which is taking place. So, I will just draw it in a better way. The metal flow will be like this. It is going like this. So, this is the inlet and this is the outlet, you are pulling like this. This is your die. So, there is a sharp change in the flow direction if the die angle is large. So, whereas the die angle was, if it was small, then you will find that okay, you will see a very smooth flow of metal is there inside the die, whereas this is your die. So, in this case with the die angle larger, the redundant deformation will be very high, and if the die angle exceeds a certain value, then you may find that there is a internal shearing of the material which can take place and forming a dead metal zone. So, suppose my die was like this, so where die angle 2 alpha is 90 degree. So, what happens when the metal is pulled, it will just deform like this, and you will find that here there is a dead metal zone where which is not going to flow at all, depending upon your frictional conditions and the die angle. So, beyond a certain increase in the die angle, this internal shearing of the material will take place. That means, your redundant deformation has to be very high, because there is an internal deformation and change in the direction of the metal flow is taking place. So, that will result in a very higher amount of energy which is required. So, in that case, so with the increase in the die angle, so as the die angle increases, so you will find that one is that as the die angle, if you are plotting this energy required for this alpha versus alpha, your plastic deformation, energy for plastic deformation remains constant. Okay. It has no relationship between the your alpha. Okay. It remains constant. But whereas with increase in the alpha, you will find that the frictional energy loss, increase in the alpha value, increase in the die angle, it decreases, because why? The contact area between the workpiece and the die material, that decreases. So, your frictional energy decreases, whereas the redundant deformation, the energy due to redundant deformation, the deformation energy, the redundant work increases as the die angle increases. So, these two things are happening. So, one is as die angle increases, What is the redundant work increases, and second is the frictional loss. Decreases, and these are the plot. So, you will find that the work for plastic deformation or homogeneous deformation remains constant, and this is the frictional energy with the diangle increasing, and this is the redundant the redundant work which increases with the diangle. Okay. So, you will find that the total energy which is required will be a sum of all these things. So, that will just keep on increasing as keep on decreasing as diangle increases, it reaches a minimum and then it again increases. So, there is an optimum diangle for depending upon your frictional component and other things. So, you have to optimize the diangle, and there are certain lot of work has been derived, and people have arrived at certain relationship for the diangle. So, a simple expression I will tell you that for obtaining the optimum diangle, okay, in a simple alpha star is approximately equal to your root of mu into your reduction divided by 1 minus r. Okay. So, this is a very useful relationship for a first hand approximation estimate of the drawing stress. That way it is very useful. Only thing is for over a large value there may be some inaccuracy, or the accuracy may get reduced with a very large value of alpha. Okay. So, in this alpha star does not depend on the precise work hardening behavior of the material or on the type of the material. That is the biggest advantage. It only depends upon your the frictional condition mu and the reduction. So, it is not dependent upon the material. That is what this relationship has come out. Okay. This is from the literature you get it. So, that means with this you can have a first hand estimate of the diangle. Now, we found that there is an optimum diangle for this. Whatever be happening, we have also arrived at different relationship for the limit of drawability for the draw stress. Okay. The thing is that most of the real material, say like there are different models, some are say maybe perfectly elastic and perfectly plastic, then elastic, plastic, elastic work hardening. So, most of the engineering material for structural use is elastic and work hardening material. So, that is what the case which comes. So, with each deformation, with each amount of increase in the strain, plastic strain, the yield strength keeps on decreasing, and that is what we get the flow curve of that. So, if this is the typical flow curve of the material given by this curve, and you will find that earlier also I am again writing that the draw stress sigma d is equal to sigma bar into 1 plus b into phi 1 into log a naught by a f. Again and again I am writing this. This is a general equation. See, this we can almost write it in this general form: sigma d is equal to 1 by an efficiency factor eta into integral sigma d epsilon. This we can write. Okay. So, where this efficiency is nothing but your ratio of plastic work, that means for homogeneous deformation, to your total work. This is the thing. So, when you look at this, the flow curve is like this, but in an ideal process this sigma d epsilon curve will come like this, but because there is a friction and redundant deformation, your the curve of the flow curve of the drawn wire will be following like this. So, that we can write it in this form as this with amount with a strain increasing. So, this will be that curve. And now, the thing is that as the material is being deformed through the die, strain hardening occurs, and if the material is severely strain hardened, the necking occurs resulting in final fracture. But when you are pulling this material for the wire drawing operation, the weakest part or weakest link, it is the point where the material exits out of the die. That is the weakest part. Inside it is compressive stresses. The other part it is already having sufficient strength, but basically at that part which is about to exit, that is the part which is the weakest material, weakest part of the link. Okay. So, for a strain hardened material, it is at that part a necking may take place when it reaches the limit of drawing. Okay. And once the necking takes place and you are pulling it, the necking is followed by a sudden fracture. So, drawing limit is reached when this condition is met. So, at that part of the exit, when the stress is equal to your drawing stress. So, the stress due to your drawing operation is equal to your draw stress, then the fracture will take place. Because beyond that, if you look at that, this is a drawing stress with a more strain, this will be higher than your flow curve, okay, flow curve of the material. So, when it is higher than the flow curve of the material, naturally that part will just deform off and then necking will start. As long as it is below the flow curve, it will not fail, because once you cross that, it is going to deform and necking will take place and it will fail at that point. It will fail at that point. So, in that case, the drawing limit, what is the drawing limit? That is what we wanted to find, where is equal to sigma d will be equal to sigma epsilon. Sigma epsilon means the from the flow curve, what is that value? When these two equals the same, then you will have it. So, if we can write that sigma epsilon is given by the Holomon relationship by k epsilon raised to n. So, this is suffix is equal to k epsilon raised to n. So, we can write this relationship sigma d is equal to 1 by eta into 1 by the sufficiency factor into sigma d epsilon. So, that will be equal to 1 by sigma k epsilon raised to n d epsilon. From this equation you will get it. So, that is equal to 1 by eta into n plus 1 into k epsilon raised to n plus 1. But k epsilon raised to n plus 1 is equal to k epsilon raised to n, that is this one, into epsilon. So, that is what. So, that means that will be equal to, so we can say it sigma d is equal to 1 by into n plus 1 into sigma into epsilon. So, we can say sigma e epsilon, oh sorry, into epsilon, and this is the condition for failure. So, that means sigma d, so this will get cancelled off. So, you will get that the maximum limit from this, the limit of drawing limit epsilon max is equal to, so that means here we can say, and this one will get cancelled. So, is equal to eta into n plus 1. So, that is the maximum limit for the drawing operation. And since this epsilon max is equal to log a b by a a, or maybe we can say this is a o by a f, starting and final. So, that is the thing. So, we can write that that is equal to, so log a naught by a f is equal to eta into n plus 1. So, we can write in this form e exponential and we also have the relationship R is equal to 1 minus A F by A O. So, that way we can write R is equal to 1 minus 1 by e raised to eta into n plus 1 R max. So, that is the limit of so that means R max, I will write it better way, that the limit of this one is equal to 1 minus exponential minus eta into n plus 1. Okay. Now, when you are having a repeated reduction through a series of dies, the n will keep on decreasing, because even though you are having repeated deformation also, the strain keeps on decreasing and work hardening keeps on decreasing. This is the general nature of the material. So, if you look at the work hardening rate versus strain, you will find that it decreases. Initially, you have a very high work hardening rate, but with the increase in the strain, it will just saturate off. So, it will keep on decreasing and then it will remain constant. So, if you want a material which is not work hardening, the best way is that you do some large amount of plastic deformation. Only thing is that ductility will be very poor, but you will get that the material is not work hardening. So, that is one way of carrying out experiments with the samples which are not work hardening, or with a different work hardening rate if you wanted, then these are the methods by which people do. So, when you are repeatedly doing reductions and other things, what happens is that the n will decrease to 0, almost to 0, and the allowable reduction keeps on decreasing in this case from this expression. Now, the thing is that if you just look at the maximum strain which is possible during the drop, if you make a comparison for the maximum strain in drawing with that of stretching, stretching means tensile testing. So, if you do a comparison between maximum strain possible between drawn wire and stretched wire. So, you will find that the strain ratio of drawing by stretching is equal to one is this eta into n plus 1 and another is n. Okay. So, why this is coming? Because in a tensile pulled sample, you will find that the maximum the necking will take place when strain is equal to your n. So, your maximum strain possible, or the strain at maximum load, at which, that is where the instability sets in, that we have discussed in the earlier classes. At the instability where it starts, that means at the ultimate tensile strength value, at that case your true strain is equal to, that means is equal to your work hardening exponent for a material which is following the Holloman relationship. So, if you just do like this, this is the relationship, and then you will find that the stretching is the effect of work hardening exponent on this drawing and stretching, how it is influencing, it is having a very high influence on the maximum strain which is possible. Okay. Now, if you look at that, these are the limits which have been obtained. Now, we will just come to the analysis of tube drawing. Okay. So, analysis of tube drawing is basically based on the plane strain conditions, and with analogy with the draw stress for wire drawing, the stress for tube drawing with a plug. So, you can say the stress for, I am not going into the derivation, detailed derivation and other thing, for tube drawing with a plug, because we found that we have discussed 4 types of tube drawing. One is the drawing with a fixed plug, drawing with a floating plug, and drawing with a mandrel. So, these things we have discussed, and sinking also. But all this drawing relationship, it is almost similar, it is having an analogy with the case of which we have discussed earlier for drawing relationship. Only difference we can say is that the sigma drawing for a tube can be approximated as one is sigma naught star, which is 2 by root 3 into your uniaxial yield strength of the material, plus instead of 1 by b, we have to put 1 by b dash. B is replaced by b dash, that is the only difference. Otherwise, so into 1 minus h a by h b raised to b dash. There are 2 things which are happening in a plug. Okay. In a plug, there are 2 interfaces coming. The interface between your die and the workpiece material, the tube material. Second is the interface between the tube material and the plug. These 2 are coming. So, you have to compensate for this thing. So, in tube drawing, in this tube drawing, no, you will find that this relationship. So, B dash in this relationship is nothing but your mu 1. So, 2 frictional constants are coming by tan alpha minus tan beta. These 2 things are coming. So, this where you will find that mu 1 is equal to coefficient of friction between tube and die material, and mu 2 is the coefficient of friction between your tube and the plug. Alpha is the semi die angle or cone angle, and beta is the semi angle of plug. If it is cylindrical plug, beta is equal to 0. So, that will come. So, if now the thing is that see, if you just look at this, you have a plug, maybe let us say a plug is like this. So, this is the die, this is the plug, and this is the die, okay, and this is your tube. So, in this case what happened? There is a friction here. So, this is the mu 1 which is coming. So, there is a friction here which is mu 2. So, this is mu 2 here, mu 1. So, this is what. So, this mu 1 is the coefficient of friction between the tube and the die material, and mu 2 is the coefficient of friction between the plug and the tube. So, these 2 things are coming, and of course, if you make different plug angle and other things, you will have die angle is same. So, that is the thing which comes. Now, if you are using that stress for mandrel, a moving mandrel, the stress for when you are considering the frictional forces at the considering moving mandrel, there are 2 things which are happening. the frictional forces at stationary die tube interface is directed towards the die entrance. Second, the frictional forces at mandrel tube interface is directed towards the die exit. This is because the mantle is moving at a velocity equal to exit velocity of the tube, whereas at the inlet it is only very less. So, you will find that with when you are drawing the operation, the material which comes out is having a higher velocity, but the inside velocity is high, but the diameter is very large, and due to which there is an accumulation of material at that side, and that is not going to affect the direction of the velocity frictional force at the die tube interface, but at the mandrel tube interface you will find that it is directed towards the exit. So, in that case now you will find that the beta dash is equal to mu 1 minus mu 2, because change in the direction takes place by tan alpha minus tan beta. See, if you just look at the previous case, you will find that beta, the relationship for beta dash is here, and that is mu 1 plus mu 2, but the difference here it is mu 1 minus mu 2, because these two are the opposite direction. And since the velocity is higher than the velocity of the metal confined in the die channel, so that is what is going to happen. The mantle is moving at a velocity which is equal to exit velocity of the tube, and it is higher compared to the inlet velocity. So, that is higher than the velocity of the metal confined in the die chamber. So, there is a forward frictional drag at the mandrel tube interface. So, this tends to cancel the backward frictional drag between the die and the tube. Okay. So, that is one advantage. That way that is going to be very helpful, because you need only less power for drawing with the mantle. If it is properly designed, then you will find that you need less power, because the forward drag, frictional drag at the mandrel tube interface, it cancels the backward frictional drag between the die and the tube. And if you say that if mu 1 is equal to mu 2, then beta dash is equal to 0, and then the differential equation you will get it as h d sigma plus sigma x plus p dh is equal to 0, which you can solve it in a very simple way and then do it in the similar way we can do it actually. Okay. So, integrating we get the equation of ideal homogeneous deformation. In this equation if you do it, so that is the condition, then simple ideal homogeneous deformation will come. So, that means if you are able to have this frictional coefficient same, then redundant deformation and that friction and those factors will be get nullified. So, you will need only lower stress which is equal to your homogeneous deformation. It is also possible for the coefficient of friction on the mandrel, that is at the side, that is a mu 2, to exceed that at the die side. So, by having a surface surface roughness and other things, or say maybe lubricating conditions if you do it properly. So, that way in such case B tend to be negative, resulting in a less draw stress than that required by frictionless ideal deformation condition. So, you may need only lesser conditions also for that case. Okay.